let's have Ashad. Ashad, let's hear from you. He hasn't got a name, you know. He hasn't got a name. We didn't give a name, you know. We didn't give a name. According to your notes, it's page 6. Page 6. It's not. This theorem basically says if something is differentiable, this means it's differentiable. This means continuous. So that theorem says on page 6, right? If something is differentiable, it will therefore be continuous. So continuity is actually a necessary condition. However, not a sufficient condition. Yeah, that theorem. Okay, example 12. Give yourself some time to try. Let's see who gets the answer. Okay, when we say the average rate of change, right? When we say average rate of change, what are we referring to? And then over the, wow, the power girl. You say you're from Malaysia, right?
Yeah.
Zhongning.
I'm Sarapan and my dad from Malaysia.
Okay, as in your school?
Oh no, I'm born and raised in Singapore.
Oh, okay. Because people from Zhongning they're quite good, you know. Malaysian school, Zhongning is quite famous. Okay, this is the average rate of change. When we say instantaneous rate of change, we refer to this. So what is f prime c equals to? After Ashad is Ivan. How or what is f prime c? Ivan? I was asking, what is f prime c? Your fx is this. So if this is fx, what then is f prime c? Right, you're right. Okay, negative tangent c. Right. And then f of pi over 4 will be ln of, what is cos of pi over 4? Anyone want to offer me? There's a yin, right? Yin. Where's yin? Not he's accelerated, is it? So therefore we have, is he here? I don't see him. Absent today. Okay, then we have his partner Tae-Yun. Root 2 over 2, right? Minus ln of 1. And then to get the value of c, right, you really need the calculator, no? If you have a calculator with you, according to what I have, right, it is approximately, you can't do this by hand, you know, you need a calculator.
How is the negative tangent?
Because when you differentiate this one, right, when you differentiate ln, right, is 1 over, then differentiate cos.
Oh, then become okay.
Right. Different cos is the minus sign. From this line to arrive at this line, it is basically calculator work. You just do it slowly. Okay. With your calculator, you will be able to evaluate to a value of c to be 0.416. That is example 12. We are now ready to move on to some theorems. Okay, let's settle for this one again. Let's settle for the pronunciation of this R-O-L-L-E. Some people say Rolly. Many people say rolls. Shall we settle for one version? Yen. How do you pronounce this? Yen. What again? Yen? Rolly. Okay. So this class prefer Rolly. In O4 they call it Rolle's theorem. What this theorem says, if it's continuous on a closed and differentiable and open, and then there's a third condition that FA equals to FB. Like for example, right? They didn't mark an A and B in this diagram. Maybe if this is your A, maybe this is your A, and maybe let's call this one. There's an A and B. There's an A and B there. There's actually an A. No, there's actually. You can see the B, but not the A. Okay. If this is the B, right? If this is the B, then my A has to be here. So can you append it? The A is there. In this case, right? In this diagram, FA and FB. So therefore, F of A is equals to F of B. So this theorem says if you have FA equals to FB and the function is differentiable, it is important for you to note, class, when a function is differentiable, Kailash is something to say? There's something to say? Okay. When a function is differentiable, it means it is smooth. So if you try to draw a smooth curve from A to B, right? You find that no matter how you draw, there will always be points along the way whose gradient is 0. And this what this theorem is all about. Be very careful, no? FA and FB need not be 0, no? They just need to be equal, right? So as long as they're equal, you will know that in between them there will always be points where the gradient is 0. Okay, let's try.
Because there's to be a turning point.
Right. Let's try example 13. Okay. Function f is continuous on the closed interval since f is a. Very good. F is then now I calculate f of 2 is equals to 0 is equals to f of 3. Your class prefers Rolle's, right? Rolle's theorem. Okay, I'm trying to say conditions. Of Rolle's theorem. Set it. Okay. Okay. So because the theorem's conditions are met, we now want to attempt to find C's which are the result of the theorem, right? So what happened is the theorem says there will be point C where the gradient will be equals to 0. Okay, Jun Xiao, is it Jun Xiao? Jun what? Sorry. Daewon's right hand side is Oppa is uncle, no, you don't breathe. Jun Xiao.
Jenny from Blackpink.
Oh, can you go JS? Easier. Okay, I'm afraid I'll mispronounce your name. JS.
You can find salt, like your salt.
This one becomes what? 2C minus 5 is equals to 0. Do you see that? You know why 2C minus 5? Yeah, it differentiated, you know. And therefore, JS says C is equals to? Yeah. Right, so that's how you can actually find C's, the value of C which are the result of the theorem. Any issues? Anybody? Okay, with example 12, let's move on to another theorem. Okay, there's another theorem here that we're going to look into, the MVT. You want to realize that the condition for the Rolle's theorem and the MVT are identical, no? That it must be continuous on a closed interval. The only difference is this theorem says the gradient of some points is equals to the gradient of the secant line. Geometrically, right, it looks like this. That between A and B, there will be points whose gradients are the same as the gradient of the line AB. If you look at this thing very carefully, you will realize that these two theorems are almost identical. No? Let me hear from, is it Infan, is it? If I pronounce it? How do you pronounce it? Infan. Ishfaq. Sorry. Ishfaq. Okay, can you tell me what do you think is the relationship between Rolle's theorem and MVT? Let's hear from him. Kailash and company, let's give our attention to our friend here. Yeah, so he's saying that the only difference is this f prime c is not 0 in the MVT. It is the gradient of the secant line. Yes, we hear you that. If I ask you this question, which is a special case of which? Is RT special case of MVT or the other way around? Shh. Let's hear from our friend. Okay, so Isha, is it?
Ishfa.
Okay, Ishfa. Sorry, Ishfa. Ishfa says what? Right, Rolle's theorem is a special case of the MVT. Why is it so? No, because you see a class, if you look more carefully, if you have the magic power, you just have to tip this diagram. You just have to rotate this diagram a little bit more. Right, just rotate the diagram a bit. MVT will also cover RT. No? You agree? No? Computationally, right? When FB is equal to FA, the numerator will be 0, is it? So actually MVT covers RT, right? So therefore RT is actually a special case of MVT. With this, let's go example 14. Okay. So first and foremost, right? They want to find, they want to apply MVT to this function f over the interval from 2 to 7. So first and foremost, you want to note this function fx, which is the square root of x plus 2, it is certainly continuous on this closed interval because the square root function is a continuous function over the interval, and the x plus 2 is also a continuous function over the same interval. It's known, right? Known. Therefore, the composition is also a continuous function. And likewise for differentiability. And because of this, we can now apply the result of MVT to this function, and we say that f prime c, there must be c such that f prime c is equals to f of 7 we said we verbalized it just now. This question does not specifically ask for it. They just say, you know. So I just assume that the question will take care of the conditions. But you're right, no, nothing stops you to be clearer, right? To establish that the conditions hold true here. That's right. So on the left hand side, after each one we have Wenyu. What is the left hand side equals to? 1 over 2 right, and the right hand side 1 over 5. So therefore you can find the value of c from here. I might be wrong in my computation. Let me know if I'm wrong.
You're never wrong.
Okay, so in this case, right, there is a value c that is 17.5. Sometimes after solving for c, there could be more than one value, and then you can confine the value of c within this interval. No, you're very careful. No, yeah. Okay. Sometimes when you solve, right, there could be more than one value. Okay. The next one is 14b. Why don't you all try 14b and then we compare answers? Okay, 14b. All try on the spot now. 14b.
Sorry,
Anyone has a first answer for 14b to compare? Brilliant! The answer for C is indeed e squared minus 1 over 2. Alright. For the left hand side, right? The left hand side is just 1 over C. And then this gives you 2 over E square minus 1. That's example 14. Christopher, is there something is there something you want to point out? Anything? Okay, good. Anything you wish to point out? Nothing, right? You get the same answer? Yes, answer. Okay. Okay, let's look at this box together. Give yourself that 30 seconds to browse through. They look quite similar, no? For non-decreasing, right? A function like this is non-decreasing. A function like this is non-decreasing. A function like this is increasing. Non-decreasing means it can plateau for a little while, and increasing means it must keep going up. That's the only difference.
So increasing functions are technically non-decreasing.
Increasing function
Are technically non-decreasing.
You're right, you know. So Brian in front here says, if you are this, you're this, right? You are surely this. It's true. Increasing is always non-decreasing, but not the other way around, no. Non-decreasing need not be. Okay. Stephen, right? Hey, your name is Stephen, really? Yeah, Stephen.
Yes.
Okay. Can you give me a function which is non-decreasing? How about non-increasing?
What?
Do you have a
Non-increasing.
do you have a piecewise, is it?
Yeah.
Like maybe like this. Right.
Yeah, the first one, but then you over.
The other way around, exactly. And then decreasing function must be something that keep going down.
Yeah.
Okay.
Something that keeps going down.
Exercise. Okay, this is for Stephen, you know. Okay, while the rest try. Stephen will tell us his views. See me. Okay, let's hear from Stephen. Stephen, true or false?
Oh yeah, that one.
Is it increasing?
No, it's one of the one.
Increasing on this? Is it considered increasing? No, is it?
Yeah. Is it? Oh shit, it is.
This function
The
is
other one is non-decreasing.
this function is increasing, no? Although it has a point where the gradient is 0, this function technically is increasing because it's only it stopped momentarily.
Yeah,
But if you move from left to right, the value keep increasing, you know. Escape function, class escape function is viewed quite the same as this kind of function. Because escape function, right, although the gradient is 0 for that one point, in the case of escape function, the value keep on increasing non-stop, keep increasing. So it's an increasing function, even there's a one point where gradient is 0.
So the only way you can make it like non-decreasing if you have a weight with
Plateau. It plateaus like this. When it's non-decreasing, right, it plateaus a little while. Okay. So Stephen got it right again. He said it's increasing. How about is it non-decreasing, Stephen?
It's non-decreasing.
It is, right? Okay. Next page. What's the next box? Is it increasing?
No. Blah, 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 blah.
This graph look like this. This graph look like this. Look like this. So is it increasing?
No. Oh.
Um,
The second one.
You have to be very careful about this example. Somehow or other, like, when I stress something in class, I just think that some students maybe miss it a bit. Yes?
Why is it increasing? Or why is it increasing also? I mean, isn't it just non-decreasing? Because at that one point, it's equal to
No. You look at the definition, right? If you satisfy this condition, you will also satisfy this condition here. So the moment you're increasing, you are definitely non-decreasing. The moment you have this, right, you will imply this. In a minute. Increasing functions are always non-decreasing, but not vice versa. I was saying, no, class, sometimes something I stress in class, you have to take note, because some other, in the grade task 1, we almost have perfect score for the whole class, almost. But for the handful who miss out something that emphasized in class, no. For the handful. So luckily, not all got full marks, otherwise I feel very embarrassed. I feel embarrassed because people were wondering, say, how come did Mr. Lin do any illegal thing? I didn't, I just,
No, if everyone gets full marks, they can say you're very good at it.
Yeah, you can.
Yeah, exactly.
people tend not to believe, no. Okay. The next box. Okay, in the next box, right? In the next box, let me ask Ethan. Are you ready, Ethan? Look at A again, look at A. What we are saying here is, if this statement is true, it will imply this statement. Okay? The question I ask you is, if this statement is true, does it imply this statement? Is the red color true? It means the other way around. If I say a function is non-decreasing, is it true? That's for Ethan. What do you think, Ethan?
I think, right?
Just say yes.
Yes.
Yeah, right. You're right. It's yes. Yeah, you're right. Yeah. As long as it's non-decreasing and it's differentiable, this thing must be true. Right? This is a truth. Okay. Okay. Next one. After Ethan is
Jason.
Raisin, right? Raisin.
Jason is against Cap.
Raisin. This statement implies. Okay, let me erase off so that it will be so cluttered. Okay. This statement implies this statement. Okay, this is what this question, this box is saying. Raisin. How about, does this statement imply? By the way, your name reminds me of this media call artist. One of the actor is called Raisin. I met him personally before. His wife, I know the wife name as Chen Liping, the husband name, I don't remember. Media call. The wife is called Chen Liping, a very famous media call artist. And the husband is, I know him as Raisin. I don't know his Chinese name. Really? Okay, so maybe you're the media call artist in the making. I think you got the look to be a media call artist. Okay, but in the meantime, come back to math first. Do you think the reverse is true? And he said no, right? He said no. Okay, he said no. Yeah, you're right. It's no. He's going to give us an example, no? Raisin's going to give us an example. It's no. Very good. You see, right? X cube graph. In the case of the X cube graph, it is an increasing function, but the gradient need not be strictly positive throughout. Okay. For part C, after raisin, it has to be yu tong. Okay, yu tong. Ask the same question again. I'm asking the same question.
Yes.
Is the reverse true?
For C.
For C.
Yeah.
And Yi Tong say yes because she saw the notes right below. There's a heading. Yeah, right. She's cleverer than others. She read ahead of time.
Wow.
Okay,
Yeah.
it's right there.
Oh.
Damn it, devil.
Raisin was busy talking with Ting Wei, so that's why he wasn't paying attention. So Ting Wei is to be blamed.
Yes.
Okay, now is okay. Now we want to read. They provided some write-up about proof though that you can read, in your free time. Okay, you can read, the proof. It's quite a nice small proof. Okay, now let's invite Ting Wei, to help her to stay awake to draw. Okay, she's gonna march the board. Oops.
Much.
And she's gonna draw. For the rest of you, try there. She's gonna come to the board and with one hand she's gonna draw. For example, 15. 15 gives you the graph of fx. You want to draw correspondingly the f prime. It's okay, just try. Yeah, it's okay, we learn together. Not to worry, Ryan is standing by. Yeah, Ryan is standing by, he'll back you up,
Yeah.
At the very least, you know that because this gradient is 0 and this gradient is 0 and this gradient is 0, right? In the f prime graph, you would expect that in the f prime graph you will hit here, and hit here. You know what I'm saying? If its gradient is 0 in the fx graph, in the f prime graph there will be x intercepts. So that's the first thing that you want to actually know. So I hope that helps a bit, Ting Wei. Oh, you didn't hear anything, okay. Great, she did it. Right, she did it. Okay. One way to go about it is, you first and foremost identify these 3 points. And then you want to know that over here, right, the gradient are all positive, right? That's why correspondingly you have positive values for the f prime graph. Can you see? There's a way to slowly navigate your way to drawing the f prime graph. Now class, I want to ask this question. Okay, it's Christopher's turn. Christopher. Wrong man?
Yeah, the
Oh.
start point, the point of origin.
Okay, yeah.
It's supposed to be to the left of the wires.
A bit more to the left, a bit more left. Okay, now.
Aiyo, big way, SMH. Aiyo.
Okay. Quick. That is Ryan's turn. Ryan, can you tell me? Can you tell me again? In the F prime graph, these are turning points, right?
Yeah.
What kind of points are these in the original graph? They are inflection points. They are inflection points. So if I were to magnify this point here, okay, if I were to magnify this point here, this point actually look like this. Okay. Christopher, can you tell me what are inflection points?
It's where I think it's where like the concavity change.
Very good. This is clockwise bending, right? This curvature is going in the anti-clockwise, where the curvature changes. And RTT, this is very important. Okay? I wanted to say out loudly and clearly. RTT, can you tell me how do we locate this one? By the way, the spelling is different if you are British or Americans.
Yeah, they use integer and with the X.
Okay, I want to hear from her loudly and clearly. How do you go about locating inflection points? Brilliant. Or vice versa, right? So she says this, and secondly, there must be a now for Chen Hui. I would like Chen Hui to give an example where the second derivative is 0 at a certain point, but at that point it's not an inflection point. Give me an example where it has condition 1 but without condition 2, and therefore it's not an inflection point. She's saying x power 4, right? She's saying x power 4. X power 4 is a good example. You try to apply this 1 and 2 to example 4, as x power 4, and you find that it satisfies 1 but not second one, And at x power 4, right? At the point x equals 0, it is actually a minimum turning point. Okay. X squared, very big example. What's x squared? X squared, the second derivative is 0, is it? Throughout, is it? No, the second derivative is how much? X squared, the second derivative is going to be what? 2. 2. It won't be 0, right? So, but you're thinking of x power 4, but when you say x squared, right? Say yes. Alright, okay. Okay, that is that graph. Ta-da! Okay, after Chen Hui, who is next? The next person has to be Zheng Hong. Zheng Hong, look up. Zheng Hong, look up. Where are you? What are critical points? Shh, don't look at the notes now. Just look up and say. Yeah, the word critical, right? Okay. Sometimes we will remember that all of us remember gradient is 0 or gradient is not defined. What you probably would overlook is Zhen Hong. What do you think people overlook? In the case of critical point, what would people overlook? People tend to overlook this one, Right? Like what Zheng Hong says, people tend to overlook that critical points must be interior points. It's a very easy thing to overlook. The telepathy, The telepathy. Okay, now play the game. Fill in the boxes.
Oh my god.
as you fill the boxes, right? I want to do a survey, you know. Do you think that teaching these days ought to be done at Starbucks instead of inside classroom?
Sorry, what?
Teaching should be done at Starbucks rather than in the classrooms.
That sounds like an English essay question.
With like better chairs and I sell like
Yeah, sofa set, then bean beds, you know. Yeah.
not really like my back.
Okay, let's see if you can fill out these boxes correctly. Okay, let's have Zhen Hong to fill the first row. Zhen Hong. What do you have for the critical points, Zhen Hong? B is correct. 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 Any more? And you're right, no more. Right, you got 4 yeses. You know, you qualify for the next round, no? And that's row number 2. you won the honor to do the second row, stationary points. Zhen Hong. What do you say? Stationary points. Good. Right. Right. Okay. Let's have I hope I pronounce correctly. Money. Money. Okay. Okay. Local maximum, please. What is your local maximum? Money. Do you say Q? Do you say Q? Money, do you say Q? Yeah, you said right, you said Q. You're right, you're right. Q is correct. Hey, money. Next one. Q is the value of the local maximum. Q. Some people put D, you know, but it's not, it's Q. The value of the local maximum is Q. Okay. Money. Minimum. S. Okay. Press on. Money.
Oh my god.
Absolute max. P. You're right. And one more. S again. And finish off the question. Points of I.
But it's Q not
没有 This guy trying to be funny. I know your name got I, but there's no I in my diagram. You know.
There's no I.
So it's the point of this question is
Inflection point.
Not Q also.
Money. C. E.
Absolute maximum.
Do you know why I use yellow color, money? Why I use yellow? Because very hard to see, right? It's true, no? If you look at diagram, sometimes inflection point hard to see, you know. If they have not indicated, right? If not indicated to us here, it can be hard to see, you know. Agree with me, no? That's not too bad, okay? Point F not too bad. You can see quite easily. But actually, if I don't point to U in the diagram, inflection point are not easy to be detected just from the diagram. That's why I use yellow to tell you that it's not easy to see. But if you see harder, you can see it. Yeah, you strain your eyes a little bit, you can see it.
So what's the inflection point? Yes.
Inflection point C, E, F. Oh yeah, okay, I'm going to write over it. C, E, F. Okay, chef. Okay, almost. Okay, let's press on. Okay. Let me ask you. In your lower years, right? How do you detect the nature of stationary points? How do you perform the first derivative test? Okay. Let me ask you. Did you use a box like that? No, you don't use like that. So that means you do it like this and like this, which is great, which is great. Yeah. Okay. So when you're asked to check for nature of station points, you have to do this, no? You have to actually check for the change in the sign of the gradient. And we are now arrived at example 16. To start off with, maybe you might want to actually write down this function as x, and it is okay, and then potentially you could then write like this now, that f prime x okay, so over here I want you to note something, no? When you get from the function f to the f prime, you are very sure about the gradient everywhere except for the point 0, because the point 0 is actually the pivotal point between one side and the other side. So writing from this to this class, I want you to know that it's legit. Okay, it's legit.
Oh, it's legit.
Because the function in fx, right, they are both polynomial. In particular, they are both linear. And for linear function, it is known to be continuous and differentiable everywhere. Okay? Now, the only contention that we have is at the point x equals to 0. Now you want to check, no? And to check for this, right? To check for this, you have to go back to basic. Then you go back basic. And then when you reach this line, you have to actually break the two calculation, You have to break into the limit when x goes towards 0 minus and then you have to also calculate the limit.
Oh, he made a bucket.
Okay, the denominator 1.
Thanks.
No one saw anything.
No one saw it.
No one saw anything.
No, sorry lah.
No one saw that.
And then you have to show that this one turns out to be, you must perform the calculation, no? And you find that this one turned out to be minus 3. You must do a calculation, no? Sorry. You can't take it from here, cannot. It's illegal. Because Aditi is thinking that why don't we do this? right? You cannot know. This one, and this one are not the same, you know. Not the same, no. It's not the same. Okay, so I point out to you not the same, so cannot. It's illegal to do that way, you know. It's only true under certain condition about function. But I realize that in your syllabus, right, it always works. And you give you and because of this, it misleads students to think that it is true all the time. It's not. One day when I can take up my collection, right, I'll give you an example where this is not valid, and the condition when this is valid. Yeah. Okay, so one thing to note, no, class, please do like this faithfully. And because the limits are different, you therefore meant to say that f prime 0 is, and therefore at x equals 0 is satisfied as a critical point, right, for this function fx. And then the question asks you to determine the local minimum value of f. You say since f prime changes from negative to positive at x equals to 0, f attains a local minimum at x equals to 0. Sorry for the clutteredness, you know. I should have done it on a blank page, you know. Since f prime changes from negative to positive at x equals 0, f attains a local minimum at x equals 0, then you got to say therefore, he asked for the local minimum, right? Therefore, local minimum value of f is equals to at x equals 0, right? It's actually 0. Because when x is 0, right? When x is 0, we know that when x is 0, fx is x, and if x is 0, therefore it's 0. Okay, so the flow is like this. Since f prime changes from negative to positive at x is 0, f attains a local minimum at x is 0, and then you can then work out the local minimum value of f. Because we want to first and foremost locate the critical points. Local minimum, local maximum, right? They typically occur at critical points. Kaita, you raise up your hand. No, just blink your hand. Okay. Some people say this theorem is extra, no? Even without this theorem, they think they know it, you know. Right, this is like extra. If two functions share the same gradient throughout, then they only differ by a constant. And then you read the example is quite straightforward. So because the two functions in example 17 share the same gradient, you can start off by writing down that one of them is the other plus a constant, and using the known conditions and the function fx, you can work out the value of k. This question wants you to find gx, so therefore you can work out gx to be just like that. Okay. Take 3 minutes break before we do our QCE. 3 minutes. Your 3 minutes starts now. Later on, I'll take a short break. You can go toilet, get a drink, and whatever. No? Okay, let's resume again. In our QCE. Okay. We have a James. Okay, James. 1A. Yep. James. 1A. What is your?
John, he lost his AirPods. Bro, thanks.
Small things. It's small
Yeah,
things.
small things.
What is the interval, James? Maybe an easier choice would have been your -3 to 3 might not work, you know. You said this right? It might not work, you know. Will it work or not? Will it work? 9 minus 3 is 6. James, I think this interval doesn't work, you know. So maybe 0 to 1 will be a better choice. Because why is it no? Because apart from the continuity and differentiability, I need to make sure that these two numbers compute to the same value. Yeah.
James, you're looking at the wrong graph. You're looking at the graph of percent rule.
Okay. Alright. James, 1B. 1B. How do you go about doing 1B, James? Now that we decided to use 0 and 1. Right. This is 0 and 1. So James says, differentiating the function, I get 2c minus 1 is equals to 0. So therefore, c is equals to half. Okay, James, since you say you have done number 2, no, we will hear you out. James, let's hear from you for number 2. What are 2 values you use? Yeah, your interval of -3 and 3 works well. And then where are the value of c? Where do you obtain the value of c? -2. This point, and this point. So from the diagram, okay.
What graph do you use like the graph of
What's it? We can't differentiate. What function is this, right? In this case, number 2, right? The function is not given to you, so I can't differentiate and do like what you did in number 1. You have to just see from the diagram.
Yeah, I know, but just asking out of interest. Just asking out of interest because like.
Okay. Ryan suggests that we try to create this function. What do you think is this function? So maybe you start off with this line. Maybe. You know what I'm saying? So you start with this function, no? And then from there, you find your fx. So I guess this potentially is that function, you know, I guess. Okay. No, because you see, the gradient is 0 at -2, at 0 and at +2. So I created this function like that, you know. I'm just second guessing. I might be still wrong. Okay, I might still be wrong.
For fx, how you find fx?
In fact, I suspect may be wrong, you know. I suspect this may be wrong, you know.
How you get a -2?
Because I know that when x is 0, the function was -2, is it? But I think it's maybe wrong, you know. The shape may be the same, but the at -3 and 3 it doesn't work, you know. I suspect it may not work. You might have to put in some factor to take care of that. Okay, anyway, I think that it's a wild guess. Okay, so Ryan has a job. At home, he will try to reconstruct this function. Okay, let's press on with number 3. Let's hear from after James is Chimaya. So you want the gradient to be, so you say FB, you're saying like FB minus 0 must be equals to 1, right? You want to find B first. You're supposed to find B first. So you're saying B, how much is B? If you calculate from here, right, one possible value for B is 2. Right, B is 2. So which means the point in question is 2, comma f of 2, and f of 2 in this case is exactly 2 also. So Chimaya suggested that in this case 3a, right, make B 2. Press on Chimaya 3b, differentiate, and equals to gradient 1, right? The gradient is 1, right? So therefore C is equals to 1 as well. You're right. Okay. Any question to raise? Didn't sleep, huh? You came back last night, right, Mason? So didn't sleep now in the morning.
I've got like a lot of things.
Okay. Number 4 will be gyro. Gyro number 4. Right. So 0 to 8, 0 to 8 is like that. So gyro says you need to draw the green line roughly here. Oh gosh, I was shocked. Sorry. Paiseh. Ethan is in high spirit, you know. It's always high, is it? Okay. Yeah, might as well, no. Better be high than low. Roughly.
Yeah, I say hello or high, right? But then it's a low and
How to pronounce this word?
He, no he.
This is also high in their language, you know.
In which language?
Anybody knows?
Chinese.
E-I.
Wait, Uganda.
Uganda.
You think you know Jack.
It's not. It's not. Swedish. Swedish. Yeah, Swedish. How can I know Swedish? I was stationed in Sweden for a couple of months last time. Yeah. I see this everywhere at the bus station.
Everywhere is gang.
Nice to be there. Nice to be there. Okay, for 4B, right, it is done similarly, right? Draw a red line, follow a green line. So question 4 requires you to guesstimate. Okay, with this, you turn over to the next page. Something that you already know, but I'm not sure you really know. Why do I ask like this though? If I were to ask you, if I were to ask you this question, why this confirms this? Is there someone who is able to march forward and tell us why this affirms this?
Privacy is increasing. So the gradient is increasing.
Okay, Yu Tong is going to march the board and with one hand. Oh, she say no, it's Gregory's turn, you know. Gregory, you have to march the board and explain to the class why this. What do you have after my lesson? I'm just curious. Greg, you know, march forward and use some diagram to explain. You cannot, Okay, Ryan wants to do it. Ryan, march the board, erase it.
Yes.
So while Ryan ponders here, you want to think, how come, long ago, I've seen even a lot of people confused with this, But in the schools, I think that most people know that if this happens, it is actually inconclusive. Some people thought that this one means inflection point. It's not. It's not. This one doesn't mean inflection point. It only means the test fails. That's all. And when that happens, you must go back to the first derivative. So Ryan and the rest of you, I am sure you are now pondering why part 1 gives you that conclusion, you know. It's something that you must be able to explain, no? Otherwise it become just adopting it without knowing the why. Okay, so you are waiting for Ryan to write down his arguments. You want to try example 18. The way to see this thing is like this, no? Okay, thank you. Okay, Ryan is trying to come up with one example to illustrate his point. Typically, people argue it from the perspective of the f prime graph, right? What happens is, if this were to be true, then the f prime graph is going upwards. The f prime graph is going upwards, right?
Yeah. So that's my explanation inside now.
Same, right?
Yeah, the gradient near the whatever point goes from negative to positive.
Right,
the gradient point is zero.
right, yeah. Just try to prove it in general that if f dot prime is positive, it is actually going upwards. So you can see from here that if this is the f prime graph, the gradient is changing from negative, like what he says, negative to positive. If the gradient changes from negative to positive, it means in the graph of fx, it is like that. Right, negative gradient, then 0, then positive gradient. That's why it's a relative minimum. Okay. And now 18. You can look into a book for 18. Okay,
Wait, I think from my drawing I accidentally made the example 18 too obvious.
really? Okay, don't let the cat out of the bag. Just be quiet. For question 18, given these conditions, you want to identify the graph. So please think about this. Okay, based on the information given, you'll find that graph B matches the condition.
Yes.
When a function is like that, right, it will also mean to say that it concave upwards, no? Class, when we say concave upwards, what do you mean? Concave upward means like this, no? Concave upwards means the graph look like this, no? Look like this. Concave upward can also mean like this, no? Or like that. Okay? So this is called concave upwards. When the graph concave upwards, you want to note that the gradient is actually increasing, and vice versa. When the gradient increases, the graph concave upwards. Many people thought that concave upwards must be the complete shape like that. No, it need not be. You know, as I drawn for you here, it could be partial, right? And likewise, concave downwards could also correspondingly mean like this. And there's a very important note here. Whenever you discuss about concavity, it must always be an open interval. If in the exam, right, you say that function f is concave, and then you write down a closed interval 0, no? 0. Because concavity depends on differentiability, you see, so that's why it can be used open interval. Read this theorem. A good example for this one, right?